Okay, so I'd like to welcome you to our second annual Number Theory Day. Our guest is Joe Silverman, coming from Brown. So Joe got his PhD at Harvard under John Tate. After appointments at MIT and BU, he moved on to Brown, where he is to this day. So in his career, he's worked in several areas, as illustrated by these books that he's written, which, if you look closely, you would see the titles run over topics from elliptic curves to cryptography to arithmetic dynamics, which is the topic that he's going to speak to us about today. So without further ado, introduce Joe Silverman.
Thank you for the introduction and for the invitation. So what I want to talk about is sort of a melding of two subjects that I really like. So let me start talking about dynamics a little bit, and just informally, what's dynamical systems? Well, or if there happen to be any differential equations people, I should probably say discrete dynamical systems. It's all about iteration. You do something, and then you do it again, and then you do it again, and then you do it again, and you try to figure out where you end up. So here is a theorem about dynamics. So start here in stores, and the operation will be travel 1 mile east, and repeat and repeat and repeat, and well, you can see the conclusion. Eventually you end up in the Atlantic. But there are lots of similar sorts of things which are much, much harder. So, for example, suppose that you have a function which will predict the weather in a little while. And you can model the weather with PDEs. So you know the current atmospheric conditions, the temperature, wind speed, everything like that. And you have a formula, you plug it in, and it gives you what the weather will be 1 minute from now. And you can do that pretty accurately. So you have this function, and you apply it again and again and again. And unfortunately, it's very hard to predict where you'll end up. I mean, you'll compute something, but in fact will not generally be a very good weather prediction. And this is mostly because it's not so much the formulas as the fact that the original measurements aren't exactly accurate. You have to sample some points in space for temperature and wind speed and so on. And they'll be off by a little bit. And eventually, when you iterate a lot of times, you get a lot of uncertainty. So people say weather systems are chaotic. A small amount of uncertainty in the initial conditions leads to a lot of uncertainty at the end. So a little more formally, a discrete dynamical system in complete abstraction with no applications at all, you have a set S, you have a function that maps S to itself, and then you just iterate S and see where iterate F and see where the points of S go. So let me set a little bit of notation. I'll write F to the nth power to mean F composed with F composed with F composed with F n times. And O sub F of alpha, that's the orbit of the point alpha, and it just tells you where the point alpha goes if you apply F and then apply it again and apply it again and apply it again. And the basic goal in dynamics usually, at least at the initial stages, is you want to classify the points in S according to what these orbits look like. Okay, and I'll talk about various sorts of behavior, but to some extent it depends what the set S looks like, what kind of structure it has. And almost every area of mathematics, you're working with some sort of category that has a set with structure and maps with structure. I don't know, a metric space in F preserves the metric, or a topological space and continuous maps, or whatever your favorite sort of space is with your favorite sort of maps. And then you classify the points according to their orbits measured by whatever structure you're interested in. And they come up all over mathematics. So just to continue with the example with weather, if the set S is all, well, let's say you have, 1,000 measuring stations measuring wind speed and temperature and wind direction, then alpha would be a list of 1,000 temperatures and wind speeds, and you'd have a function that would then predict what the temperature and wind speed would be at each of these spots a minute from now. And that'll be pretty accurate. If you create such a function and do it 60 times, you'll get the weather at all of these measuring stations in an hour, be fairly accurate. So 4,320 minutes is approximately how long it is between now and Saturday. And that would be much less accurate. Although, in fact, these days, 4-day forecasts are getting reasonably good. 40-day forecasts are not much better than picking them out of a hat. So here's another example of iteration that has been vastly generalized and is used in all kinds of mathematics. If you have a function, this capital F of x, and you're trying to find someplace where it vanishes, or solving an equation, which is one of the basic problems in mathematics. So what you do is you create this other function, x minus f of x over its derivative. So I'm assuming capital F is reasonably nice, has a derivative. Then it turns out if you start even reasonably close to a root of capital F and iterate this function little f, then you'll frequently converge to a solution. And in fact, once you get reasonably close, you'll converge very rapidly, quadratic exponentially, which is very nice. And this gets used for applications out in the real world. It also gets used for all sorts of theoretical constructions, including at least one recent Fields medal. Super generalization of this, but the underlying bottom idea was this: to create solutions to certain differential equations. So iteration is useful for various things. Classical dynamical systems, discrete dynamical systems, often iterates polynomials, which are in some sense the simplest sort of functions, or more generally, well, people start with quadratic polynomials, or more generally higher degree polynomials, or rational functions, which for simplicity I probably won't talk about much. But anyway, so you have a polynomial and you can plug in real numbers and see where they go under iteration, or you can plug in complex numbers and see where they go under iteration, and you get this beautiful theory which dates back quite a ways. The complex theory really, the deep theorem started getting proven in the 1920s. So I'm going to stick to polynomials of one variable for this talk, and I'll always assume they are polynomials of degree at least 2. A lot of what I'm going to say is also true for rational functions, so quotients of polynomials. Some of it is true for multivariable maps. So anyway, here is the absolutely simplest nonlinear function. At least, yeah? Anyone want to propose a simpler nonlinear function? Okay, so just the squaring function. And its dynamics is pretty easy. So for example, if I start with 2, and I square it, I get 4, and I square it, I get 16, I square it, I get 256, and so on. It just heads on out to infinity. If I start at a half and square and square and square, I'll head in towards 0. There are other sorts of behaviors. If I start at 0, it doesn't move. So 0 is a fixed point. There are points like -1 that move, but they then end up in a cycle, at a fixed point, in fact. You can also get points that sort of cycle around but aren't fixed. So here's an example. That's a primitive cube root of 1. And f just reverses these 2 points. So you get a 2 cycle, and you just go around. So the points which cycle, that come back to where they started, are called periodic points. And the period is the the smallest number of iterates you need to get back to where you started. And a lot of the talk I'm going to be talking about periodic points. In many situations, the behavior of the periodic points tells you a lot about the dynamics of all the points. Well, not surprisingly, a fixed point is called a fixed point because it's fixed. A point's called pre-periodic if, well, it doesn't have to return to where it started, but eventually it has to end up in a loop. So you kind of have a tail maybe and then a loop. Or another way to say that is the orbit is finite, which means eventually, of course, it has to sort of loop back on itself. So there are these periodic points and pre-periodic points. And points that do not ever loop around and go into a loop are called wandering points. So those are points whose orbit is infinite. And the examples for z squared give examples of all of these. So 2 and 1/2 are wandering points. They never loop. 0 and 1 are fixed points. -1's pre-periodic, but it's not periodic because it does end up in a loop, but it's not actually in the loop itself. It's in the tail part. So -1 there would go to 1, which then loops. And that cube root of unity is a periodic point. It has period 2. Okay? So those who have been to talks on complex dynamics have seen lots of pictures like this. So if you take a polynomial and look at it as a map from the complex numbers to itself, or sometimes people throw the point at infinity in if you're using rational functions or meromorphic functions or things. You get all this really cool behavior. You get these beautiful pictures. The one on the left is the famous Mandelbrot set. The one on the right is what's called a Julia set of a certain quadratic polynomial that I don't even remember which one it is. The points are colored according to escape rates or whether points escape to infinity or don't escape to infinity or whatever. You notice I'm waving my hands because I'm not giving you any details. And the reason for that is these pictures are gorgeous, but I want to do number theory, and so we're not going to have any pretty pictures. But we'll have lots of numbers. So I hope people like numbers. All right. So number theory in dynamics is come to be referred to as arithmetic dynamics. And instead of studying what orbits do according to, like, do they go out to infinity or do they come together or whatever, we look at the number theoretic properties of an orbit. And it's quite a young field, which is nice. It means there's lots of interesting things to work on and to prove. It really got going during the late 1980s and 1990s. A bunch of people sort of started working on this to some extent independently and then kind of coalesced into this field of arithmetic dynamics. So I want to talk about, rather than sort of big broad survey, I'm going to concentrate on 2 particular problems to give you a flavor of what the field is like. So the first topic will be rational numbers that are periodic points. So the rational numbers is the number theory, periodic points is the dynamics. And the second is orbits over finite fields. So orbits are dynamics and finite fields, sort of, well, at least algebra, and somewhat number theoretic. So this is how a number theorist kind of looks at periodic points. And I'm pretty much just going to talk about quadratic polynomials till right at the end. So it turns out, I mean, this may look special. You can always change variables, sort of in a dynamical sense, that any quadratic polynomial basically looks like this. So it's enough to just study these. That's why the dynamics people also just use this family. So for each number c, you get a quadratic polynomial, and we can start iterating it. And so here's the first question. How do we actually find periodic points? Well, the fixed points are the solutions of f of z equals z. That's what fixed means. So it's the equation z squared plus c equals z. And that's a nice quadratic equation, and there are the two solutions. So there are two fixed points. Well, except in one case where there's one fixed point that's a double root. All right, how about points of period 2 that are two-cycle? So I need to take f of z, which is this polynomial, and set it equal to z, and then solve. Okay, except that's not quite right. Because that'll give me also, it'll give me points of period 2, it'll also give me fixed points of period 1. Because if you have a fixed point, and you apply f twice, obviously, you apply f once, it stays the same. You apply f again, it stays the same. So I want to get rid of the fixed points if I'm really looking for just points of period 2. So what I need to do is take f of z minus z. So that's all the points of period 1 and 2. And then divide by f of z minus z to get rid of the points of period 1. And if you do that little algebra, you get that quadratic equation at the top. And it has these two solutions, so you get these 2 points of period 2. Okay, except again, this is a little bit of a lie. If you actually end up with a double root there, the period 2 points coalesce to become a fixed point. And this phenomenon is the beginning of what makes the Mandelbrot set so complicated, in fact. But anyway, but roughly speaking, you should get 2 points of period 2 for these quadratics, except in this one case. However, there is a square root there, right? All right, so let me do one more thing. How about period 4? Well, I would want f to the 4th of z minus z, the thing way at the top there. Those will be points of period 1, 2, or 4. So I have to divide by the points of period 2 and 1 to get rid of them, and you get this 12th degree polynomial in z, and you set it equal to 0, and you'll get, well, except for a few c values, you'll get 12 different points of period 4, at least over the complex numbers, right? So being a number theorist, I tend to think of c as being a rational number, but nonetheless, you're going to get this 12th degree polynomial. You'll get, you won't just get rational solutions. So in general, this quadratic polynomial will have lots and lots of complex points of period n. This requires a little bit of proof that you don't get high multiplicities in these things. And it's in fact easy enough to write down examples where you'll get lots and lots of real points of period n. So if you're doing complex dynamics or real dynamics, you get lots and lots of periodic points. But as a number theorist, if you want to work over the rational numbers, you can ask how many of these complex or real periodic points can actually be rational numbers. Okay? And that's the question I want to ask. So let C be a rational number. And for the polynomial z squared plus c, how many of its periodic points are actually rational numbers? Okay? This is a nice but quite hard exercise if you want to assign it to like a number theory class without giving them any hints on how to do it. Turns out it's a special case of a theorem of Northcott's. The answer is only finitely many. In fact, there are only finitely many pre-periodic points that are rational numbers. This isn't so clear. So here's an example. C squared minus 29 over 16. Its rational pre-periodic points are these 8 values. Which fit into a really nice pattern, 1, 3, 5, 7. I really don't know why that happens, actually. And it's also clear that if a number is periodic or pre-periodic, then its negative is, because right? When you plug it in, the squares will go to the same place. So, and a dynamicist probably would say there are 9 preperiodic points, because they'd also include the point out at infinity that's fixed by z squared. So depends if you like the affine line or the projective line. But anyway, here are a pretty significant number of rational preperiodic points. And on the poster for the conference, there's a picture, I'm pretty sure of this one, that shows you where each of these points goes with a nice little diagram, which was created by Bjorn Poonen. And for those who are, I guess it's a very mixed audience there. I've got undergraduates who I'm trying to make the talk comprehensible for all the undergrads, so I hope I have. But I did want to make an occasional comment addressed to some of the faculty members, maybe. Northcutt's theorem, which was actually dates back to 1950, is much more general. It says that if you have a morphism of projective space of degree at least 2 defined over a number field, then there are only finitely many preperiodic points defined over that number field. So it's pretty general. Interestingly, this theorem was... It is effective, yes. Though the bounds are pretty big, but yes. Yeah. Northcott published this theorem, and then no one noticed it. And there are a number of papers from the late 1960s and on into the 1970s proving special cases of this theorem without referring to Northcott, which is weird because he didn't publish it in an obscure journal. It was in the Annals in 1950. Anyway, but people did finally realize that. So this is now called Northcott's theorem rather than crediting it to some of the other people who reproved it. Okay. So every math talk's supposed to have a proof in it, so I'm going to sketch the proof of Northcott's theorem, at least for the polynomial z squared plus c. I hope everyone knows where the quote comes from. So the idea, in some sense, goes all the way back to Fermat. It's kind of sort of some of the stuff in Alvaro's talk, where what you do is you create a way to measure how complicated a number is, and then show that the map, the function f, makes numbers more complicated. But if it's periodic, it can't be getting more complicated because it has to loop back around and become less complicated. Okay, so it's a version of Fermat's descent, essentially. So the way we measure how complicated a rational number is we take the maximum of the numerator and the denominator. Okay? People often take the log of this, which would just be basically the number of bits, roughly, it takes to write the number down. And here's a key fact that's completely trivial. There are only finitely many rational numbers if you bound the height. Why? Well, because the tops in a and b are integers, and if you bound the size of integers, there are only finitely many of them. This underlies an immense number of proofs in number theory, and it comes down to the fact there are no integers between 0 and 1. Amazing. Okay. So here's a key lemma. And this is the f makes things more complicated lemma. It basically says that f of alpha is the square of, the height of f of alpha is the square of the height of alpha, up to some constant there that doesn't depend on alpha. And this is kind of what you'd expect. If you think of a over b, and you square it, and add something, well, you add something, forget about that. If you square it, the numerator gets squared and the denominator gets squared, so the complexity, the height should get squared, because you're just squaring the numerator and the denominator. You just have to worry about cancellation. Anyway, here's the proof idea in smaller type that you're not supposed to read, and I actually have a final slide that has the full details that you definitely won't want to read, but I will throw it up there later. Here's how the proof goes using this lemma. So suppose that alpha has period n. Well, that means that the height of alpha is the same as the height of f to the n of alpha, because f to the n of alpha equals alpha, because alpha has period n. Now we apply the lemma. I think of f to the n of alpha as f of f to the n minus 1 of alpha. Right? Yeah, that's the place to write it. So applying the lemma, but instead of alpha there, I put f to the n minus 1 of alpha, I get a lower bound where the key height thing gets squared. So the height of f to the n of alpha looks like the height of f to the n minus 1 of alpha squared. And I do it again, and it gets the fourth power, and so on. Now, I know there's this annoying constant out in front that's getting smaller, but you keep track of it. And if you just do this, and well, you have to sum a partial geometric series, but after n steps, you'll get down here. And this is really strange, because you have the height of alpha on the right-hand side, and you have the height of alpha to this huge power that's smaller. So you just do a little algebra with this, and what you end up with is that the height of alpha is less than the square of the height of c. So there are only finitely many possibilities for alpha, independent of n, independent of the period. So someone asked about effectivity. Here's an extremely effective bound for this example. And in general, you can write down similar bounds. OK? Great. There are a lot of theorems in number theory, ranging from relatively elementary to extremely deep theorems, that say you have this interesting set, group, module, whatever, and it's finite. And the natural next question is, how big can it be? So we now know that if c is a rational number, then z squared plus c has only finitely many preperiodic points that are rational numbers. How many can it have? Well, there are infinitely many choices for c, rationals, so that z squared plus c has a rational fixed point. In fact, here's an example. If you take any alpha that's rational, let c be alpha minus alpha squared, then alpha will be a fixed point, because you just plug it in and it's a fixed point. So that, well, that's interesting. So you can get infinitely many choices for c that are rational with a rational fixed point. Period 2, you can play the same game. If you let alpha be any rational number, and let c be minus 1 minus alpha squared, then z squared plus c has alpha as a point of period 2.
Period 1 or 2?
No, it'll be period 2, except maybe for 1 or 2 choices. Yeah. Actually, for most, there's just one choice, I guess. That, yeah. Period 3's a little trickier. And this is actually a very nice exercise that requires a bunch of algebra. So if you take alpha to be any rational number where the denominators here don't vanish, OK? And you take the quadratic polynomial z squared plus this horrendous-looking rational number, then this rational number, if you plug it in, will have period 3. Okay. And it's a big algebra exercise to do this. There are clever ways to do it and less clever ways to do it. And one of my students was trying to do it the less clever way and said that Magma or Sage, whatever he was using, was objecting. OK. So we now know that for period 1, period 2, and period 3, there are lots of rational values for c that give rational numbers with those periods. How about period 4? Well, this is that equation I had up before. So to find a c value that's rational and a starting alpha value of period 4 that's rational, that means finding a solution to that equation in the yellow box with C and Z being rational numbers. Well, that's an equation of a curve. If you think of C and Z as your two variables, and you're asking, are there any points on this curve whose two coordinates are both rational? And this is a very classical kind of question. Given a polynomial equation in two variables, does it have solutions in rational numbers? Innumerable amounts have been written about it. And there are a lot of techniques that one can apply to this. And this particular equation that looks kind of messy turns out, for those who know what it means, to have genus 1. But in any case, Patrick Morton proved that it has no solutions in rational numbers. Okay. Again, for those who know a little more, there may be a singular point or two on here which doesn't actually correspond to period 4. And if you take the projective completion, there'll be points out at infinity that don't correspond, that correspond to C equals infinity, which aren't really allowed. Anyway, so, but what Patrick did was he converted this into a standard looking elliptic curve and then looked it up in a table. It turns out it's x1 of 16, I think, something like that, which happens to have rank 0. And, anyway, he proved that, so you cannot find a rational C value and a rational starting value that gives a square, that gives a four cycle. All right, how about 5 or 6 or so on? Well, so Morton said you can't do period 4. Flynn, Poonen, and Schaefer about 5 years later showed you can't get period 5. And at the time, this was a real tour de force. It required, again, for those who know a little bit of the theory, it required finding all the rational points on a curve of genus 2, which these days has been mechanized to the extent that all the packages, algebra packages will do this very quickly. But at the time, they did it by hand. There had been very few examples where people had computed everything. And then Mikhail Stoll, about a decade later at an AIM conference, where I think he may have first learned about the problem, by the end of the week had managed to at least sketch how to do period 6, and then he subsequently finished it, except I'm lying again. So this is partly my way of giving praise to Donald Knuth, who's, I don't know if anyone's read the tech book where he actually described, well, what became LaTeX, but it was just tech at the time. It's full of footnotes and it's full of lies, but they're very helpful lies. And he says that. Anyway, so this isn't quite true. What Stoll did was he proved you can't get a point at period 6 provided Birch-Swinnerton and Dyer is true for a certain abelian variety of dimension 4, which was just which is too big to actually do a descent on directly. Anyway, but we all believe Birch-Swinnerton and Dyer. So. No, the rank is not 0. He needs to know the rank is, I think, 2, which is less than the dimension which lets you use Chobot-Coleman to find all the rational points on this curve. Yeah. It's, again, a computational tour de force. He's just amazing with this stuff. But you can't, the numbers are just too big to do a descent. There's no rational 2 torsion, for example, to use. So anyway, that's as far as we know. But this didn't stop Poonen from making a rather bold conjecture that, in fact, I don't know. I guess this is pretty bold given the fact that at the time only 4 and 5 were known. But he conjectured that, in fact, you can't get a point of period n for a quadratic polynomial over the rationals of period 4 or bigger. And assuming that, he could then describe all the possible pre-periodic pictures you could get, and that's what some of the pictures on the poster are. Yeah. So the conjecture is kind of bold, but the nice thing is he then proved that if the conjecture is true, then you can never have more than 8 rational pre-periodic points. And I gave you an example earlier which has 8. And up to equivalence, there are essentially 2 examples. Do you have a question? No? Okay. Yeah, so Punin's conjecture, so that was 1998, but that was about 10 years after Patrick Morton and I had made a general conjecture that isn't as precise as what Punin conjectured, but far more general. Well, you said it's just 4 years earlier. Okay, I don't know why that says d greater than or equal to 3. Replace the 3 by a 2 there. So let d be an integer at least 2. Then there's a constant depending just on d, so that for any polynomial of degree d with rational coefficients, the number of rational preperiodic points is bounded by c of d. So it's independent of the polynomial. It just depends on the degree. So Punin's conjecture for d equals 2 is that c of 2 is 8. I think there's a guess what c of 3 is, but I don't remember it. And the original guess of what c of 3 was wrong, because then people found some bigger ones. It's actually quite tricky searching for examples. And actually, much more generally, and again, this is for those who know a little algebraic geometry, for all number fields of bounded degree and all morphisms of projective n space of a given degree, the number of preperiodic points. So this side is what Northcott says is finite, should be bounded independent of f, and the dependence on k should just be on the degree of the number field. Okay. And this is a pretty powerful conjecture. The very special case, d equals 1, n equals 1, little d equals 4, implies a theorem of Mazur's about torsion points on elliptic curves over Q. That's a very, very deep theorem. And from this conjecture in that case, the proof of Mazur's theorem is like 3 lines. So I'd be very surprised if there was an easy proof of this, but hard proofs would be nice too. So this is a uniform boundedness conjecture. So how are we doing for time? Not bad. Okay, so the second problem that I wanted to talk about to illustrate the sort of things that people look at in arithmetic dynamics is dynamics over finite fields. And again, most of this would be true for any finite fields if you're used to them, but I'll just stick with the integers mod p, where p is a prime, so that collection of finite fields. And we can look at dynamical systems of the integers mod p. And again, you have a polynomial, you can plug in a mod p number, get out a mod p number. So I'll let f sub p, too many f's. Blackboard bold f sub p is the integers mod p, it's a field. And we'll take a polynomial with coefficients in this finite field, and then it maps the finite field to itself. And there are all kinds of questions you can ask. One question people have asked for ages is, when can you find primes p and polynomials little f so that that map is a bijection, is 1 to 1 and 1 to? Those are called permutation polynomials. There's a whole literature of permutation polynomials, books and hundreds of articles. It's not what I'm actually going to talk about, but it's an interesting subject. But let's start with the question. So, right, there are points that are periodic, there are points that, well, pre-periodic means finite orbit. So which points are pre-periodic? Which points mod p have finite orbit? Yeah, so some people have, yeah, all of them, right? Because there's only finitely many values. So pigeonhole principle, eventually it's got to repeat. So there's a very easy theorem. Every point over a finite field is pre-periodic. But they're not all periodic. They don't necessarily come back to themselves. They might be on a tail that ends up in a loop, right? So here's an example. Let's look at z squared plus 1 working mod 17. So I have 17 numbers, and I can just sort of graph where they go by putting an arrow from number to number if f maps number to number. And this is what it looks like. So the dynamical system of z squared plus 1 acting on the finite field with 17 elements has, so people call this a dynamical graph. So there are 6 periodic points. It's this hexagon in the middle there. And then there are another 11 points that are strictly pre-periodic. So they're on the tail. They're not periodic. So this leads to an obvious question of, well, how many periodic points are there versus the ones that are strictly pre-periodic? But as soon as you start drawing these graphs, another thing jumps out at you. So here's another example, z squared plus 2 working mod 31. There's the graph. It's disconnected. So there's 2 pieces. And there aren't very many periodic points here. There's a 3 cycle up on the top, and there's a 2 cycle in the middle, in the bottom one, 9 and 21. So there are 5 periodic points, a 2 cycle and a 3 cycle, and 26 strictly pre-periodic points, and the graph's disconnected. It has 2 components. So that's another question. I mean, are the graphs connected, disconnected? So I actually don't have answers for any of this, but they're really interesting questions. People have been working on them. So first, let me define the periodic point exponent. So I hope this makes no sense. So you look at the number of points which are actually periodic, okay? And basically, I want to write that as p to a power. So that's what I get by taking these logs here. So if that periodic exponent, for example, is a half, it means about square root of p points are periodic, and the remaining ones aren't, which will, in fact, be the likely thing. And let's define comp of f to be the number of components. So for those 2 examples on the previous slides, for z squared plus 1, about, well, this was over, so 17 to the 0.63 power is how many periodic points there were. And on this one, about 31 to the 0.47 power, about the square root. And mod 17 for that polynomial, there was 1 component. Mod 31 for z squared plus 2, there were 2 components. So what would the typical sizes be? Well, this is actually a question that people have considered, not for polynomial maps so much, but if for all maps. So suppose I look at all the maps from FP to FP. I mean, or more generally, all the maps from a set of n elements to a set of n elements. There are 2 to the n different maps, right? So look at all the maps. Forget about polynomials or stuff. Then the average exponent for the periodic points is 1/2. In other words, roughly the square root of the number of points will, and the number of components on average, and these are theorems, is roughly 1/2 log of the number of points. The typical behavior is you have one really big cycle of size about square root of p, each of which has about square root of p each of which has a tail of length square root of p coming into it That eats up everything. And there's this extra sort of log p components which are small. However, random maps are not, so for a random map, you have about square root of p periodic points and about 1/2 p log p components. And I got a lot too far there. Okay, but polynomial maps are not random. In particular, for example, if you take a polynomial of degree d, then the inverse image of a point has at most d points in it. And there are stranger things that happen too because of ramification, and if a polynomial has all but one of its roots rational, then the last root is rational also, and things. So I just want two conjectures, which is probably not readable, but if I say it in words, it will be. This says that even if you just look at polynomial maps of degree d, one would expect about square root of p periodic points, and the rest of them non-periodic, as the prime gets larger and larger. What's known is that if d is pretty big compared to square root of p, then this is more or less correct. This is a theorem of Flynn's and Garton's. Interesting, this actually, and the next slide also has another theorem of theirs. This came out of a project that they started at an Arizona winter school, in fact. So it's very nice. And similarly, for connectivity, again, I wrote it out so that it's actually formally correct. But what it says is that if you look at all the polynomials of degree d, then you'd expect to have the right number of components as p gets large. In other words, they behave like random maps. And again, Flynn and Garton prove something close, well, they prove a lower bound. If, you see, you can't let p go to infinity here, because p has to be less than d squared. But you can kind of let p and d go to infinity together and they get something. So it's a nice result, but much weaker than what's probably true. Very good. So let me close with one more finite field example of a question, again, that I don't know the answer to. But this is another standard sort of thing that people do in number theory. Suppose I start with a polynomial with integer coefficients, and I take an integer that's a wandering point. So it just gets all these points. Well, I can reduce mod p and see what happens for different primes. So here's an example. So for z squared plus 1, if I start at 0, 0 goes to 1, goes to 2, goes to 5, goes to 26, goes to 26 squared plus 1 that I can't do in my head. So it just gets bigger and bigger. But if I reduce mod 3, I get 0 to 1, and then it hits 2, which is a fixed point. If you reduce it mod 5, you have a 3 cycle. If you reduce it mod 11, you get 6 different points, but it ends up in a 2 cycle, and so on. Okay? So the question is, what's the behavior as p gets big? And I don't even know a precise conjecture for what one would expect here of. I mean, I think you can, well, actually, I don't know. So that's the question, is as p gets larger, how does the size of this orbit vary? In this case, it goes 3, 3, 6, 8, 6. So it's not increasing necessarily. Does it go to infinity? Yeah, I think that's probably provable, but how fast? And quantitative estimates for how many points there are would be very interesting. And again, maybe addressing some of the number theorists in the audience, a lot of the conjectures and problems in arithmetic dynamics are analogs of things in arithmetic geometry. So, I mean, this is a direct analog of take an elliptic curve over Q. How does it behave when you reduce mod P as P varies or P goes to infinity? So we're just taking a dynamical system over Q, and how does it behave? And you can ask the same thing for the number of components or whatever. Okay, so here's the proof of Northcott's lemma. I will give you 3 seconds to look at it, and then there will be a quiz. No, anyway, so it's basically, it's some algebra and some inequalities, triangle inequality. And you've got to worry a little bit about cancellation between numerators and denominators, so there's a GCD calculation too. Anyway, so I want to thank you very much for inviting me to give this talk, and thank you.
Any questions from the speaker?
Yeah.
So on the elliptic curve side, there is the Sato-Tate conjecture. Is there something that sort of maybe related to what you were just speaking about? Is there some bigger formulation of Sato-Tate in the
Not exactly. Yeah, the problem is Sato-Tate comes from the fact that you've got this nice two-dimensional representation. Then you're taking traces. And this is coming from the fact that the torsion points on the elliptic curve form a group. If you do something similar with periodic points, you'll get Galois extensions, but the groups you get are Reith products, so they don't have this nice structure. I mean, the representations aren't really so clear what to do. The other thing people do is they'll take a starting point and look at the inverse images and look at the Galois extension. So this is like Kummer theory. And again, it doesn't look quite like the elliptic curves. The Galois groups sit inside tree automorphism groups. So you get analogs of Sayre's open image theorem, that the image of Galois in this tree automorphism group should be finite index, except in the cases where you know it's not. So they're analogs of that theorem, but Sato-Tate, people have thought about it, but not so much. There really isn't an analog of Mordell-Weil either, is the thing, again, because the iterates of F form a semigroup, while an abelian variety is a group, and get this extra structure.
Other questions? Okay, we're still